Hello there, welcome to Learning of Engineering tutorial video lecture. In this video lecture, we are trying to learn what is the thermal stress and how it is affected on the solid bar. As we know, when the temperature is going to be rising and falling, then this situation we are going to be calling temperature gradient. If the temperature gradient is varying, so then automatically the solid member is going to be subjected to certain kind of expansion and the contraction. If the temperature is rising from room temperature to the high temperature like 60, 70, 100, so then automatically the solid material will going to be start to elongating. And similarly, when the temperature is going to be reducing from room temperature to the below, so then what will happen? That material will going to be start to contracting. So on that basis, we have to design the engineering structure so that it can going to be withstand. For example, the railway tracks are there. So in that case, what will happen? So always at the summer time, the elongation is going to be taking place. In winter side, a contraction is going to be taking. In order to compensate this one, when they are going to be joining the two tracks over there, so then what happens? There is going to be a gap they are going to be maintaining. So that's they are allowing for the free expansion. So then it will not change the shape and size of the component. If the tracks are going to be laid in a straight line, but due to the thermal stresses, what will happen? They are going to be uneven shapes are going to be forming. That's because the free expansion is going to be restricted. So I hope you are able to understand the importance of the thermal stresses to study in the mechanics of solids. Now we can see here, I have taken a one solid bar. So that is going to be end A is fixed and B is going to be allowed for the free. And it has a length L. And similarly, it has a cross section also available. The cross section may be here. We can take the circular cross section or the rectangle or maybe the square cross section. So whichever you are comfortable. So now I am going to be taking here, that's going to be L is the length of the member. So then what I am going to do, I am going to be made to subject it to the temperature over here. So before going to that, we can see here, L is the original length of the system and the T is the rising temperatures that I am going to be taking T1 minus T2. The T1 is the existing temperature on the material and how much you are going to be increasing. So next, E is the Young's modulus of the system. We know every material has its own Young's modulus. Alpha is the coefficient of linear expansion. This is widely using for the thermal conditions. Del L is going to be elongation of the bar. So there we can see A is going to be your cross sectional area. Now it is subjected to the certain temperatures. So then what will happen? Can you see NDA is fixed and B is going to be allowed freely. So this we have taken as for our mathematical requirements. So then what will happen when the temperature is going to be rising, right? So automatically due to this thermal expansion of that material, it's trying to move in the forward direction. That means it is trying to move in the direction of the longitudinal axis. So then what happened? It is going to be reaching to the next level. So can you see this elongation? I can say it is going to be the del L. Right? So this del L is going to be because of this thermal expansion. So then automatically it is going to be elongation is taking. So then what will happen? Then how could you calculate here is the thermal expansion? So the thermal expansion del L is equal to here, that is the elongation due to the thermal stress is equal to, we are going to be taking the parameter of your, so the coefficient of linear expansion, right? And the rise in temperature and the total length we are going to be multiplying here. So that is going to be alpha, right? And change in temperature into the length of the object. So then automatically we are able to calculate the change in dimensions. But what I am going to do, if I am going to be, I am not interested for the free expansion. So then what I am going to do, I am applying the force in the opposite direction. So then what happened, the same figure I am taking over here. So this is going to be your object and it is going to be elongating. This is the assumption. This is the L and this is the del L we have. So now what I am going to do, I am applying the force from this direction. So that means I am trying to push that object in the opposite direction because it is expanding in this direction. So then this force is going to be allowing, that is this force is not allowing for the free expansion. So then what will happen? When the resistance force is going to be developing for the free motion of the object, then the stresses are going to be developing inside the material. So then how we are going to be calculating here is the load P. So then what will happen? That finally it will going to be reached to its original position. So when I am going to be applying the force, then I am not allowing to move in the free direction. So then it is going to be a constrained motion, it is going to be existed. Now we need to find out how much amount of the load we need to apply to restrict the free expansion of the system. So once we calculated, here is the del L, I am going to find out the thermal strain. So here is the thermal strain, epsilon I am going to be considering, right? So what is the epsilon? Change in dimensions to the original dimensions we are going to be calling. Here what is the change in dimensions we are getting? So that change in dimensions here is going to be the change in dimensions by original dimensions. So how we are going to be find out the change in dimensions? There we can see epsilon is equal to, that is going to be thermal strain is equal to the final length of the system minus initial length of the system by initial length. So what is the final length we do have? That's going to be L plus del L is going to be the final length of the system minus L is going to be the initial length of the system, that's going to be the L divided by initial length we are going to be taking. So from this one, epsilon, that is going to be L will going to be cancelled, then finally we have del L by L. So this is going to be the strain we are going to be calculating. So then what happened? The del L also we can calculate from epsilon L also. So this is the way we are going to be calculating del L. Suppose if I want to define the del L in terms of the stresses, we know the Young's modulus is equal to the this is going to be stress by strain we are going to be getting. So if I am going to be substituting in this equation, so that I can calculate that part also. The del L is equal to, so that's going to be the sigma by Young's modulus, that is the thermal stresses into the length we are going to be considering. This the way also we can determine the change in length of the system. So here we can see epsilon is equal to del L by L, that I am going to be del L, we do have alpha T into L, that I am going to be substituting here. This is the epsilon is equal to alpha T L by L, we got it. L will going to be cancelled. From this one, epsilon is equal to alpha T, we got it. If I am going to be substituting in this equation, so that we are also going to be getting that value. After determining the strain effect, now we can see we need to find out the stress effect, that is going to be thermal stresses. The thermal stresses from we are going to be calculating Young's modulus is equal to stress by strain. So then stress is equal to Young's modulus into strain. Then strain values I have substituted in this equation, that is the sigma S is equal to alpha T E, right? So once I am going to be calculating the thermal stresses inside a single bar, now I want to find out how much amount of the load is required to restrict the free motion of the object. So then from this one we know the stress is equal to load by area, that is equal to P is equal to sigma S into A. We know the thermal stresses how much it is going to be, that I am going to be substituted here. Then final value of the load is equal to alpha T E A we are going to be getting. A is nothing but the cross sectional area of the member, that's maybe in the circular cross section or maybe the square cross section, rectangle or elliptical cross sections also we can see it. So I hope you are able to understand over here.